In this lecture, we're going to provide a review of viscoelasticity and the inherent properties of, biological tissues with respect to viscoelasticity. And so when we think about viscoelasticity, biological materials and biological tissues are better described using these properties, which includes something referred to as hysteresis, which we'll define shortly, strain rate sensitivity, stress relaxation, and creep. Now, before we get into viscoelasticity, when we talk about elastic, or rather non-viscous materials, these are materials that have the ability to store energy from a deforming agent and to return the same amount of energy during the recoil phase. And so when a material is stretched, compressed, twisted, or bent, it is deformed, and as long as that material stays within its elastic range, the amount of energy, mechanical energy, put into the deformation of that material gets restored during unloading in the same manner. Now, when we talk about biological tissues, these are quite different because biological tissues have, to varying degrees, a fluid environment. And as a result, fluids do experience a resistance to fluid flow, and that's dependent upon the inherent molecules that make up that fluid, and the rate of movement of that fluid. And so when we talk about viscoelasticities, we're combining elastic properties and the viscous nature of that fluid-based tissue. And as a result, when we talk about the response to loading of biological tissues, it is time rate based. So depending upon the rate at which we apply loading to tissues, whether it's stretching, compression, bending, or twisting, the response to those materials will be dependent upon the rate of that loading. And so when we talk about the first basic principle of viscoelasticity, which is hysteresis, we'll start with the figure up on the top left-hand corner of the slide. And here we see our typical stress-strain relationship of some type of material. And what we see here is that as we load that material, as we attempt to stretch or bend that material, it will deform, and then at the very end here of this profile, the loading is completely removed and the material will return back to its original length. That's the relative measure of deformation, strain. So purely elastic materials, provided that the deformation stays within that elastic range, tissues are considered to be, or materials and tissues that are purely elastic are considered to be resilient. There's no loss in energy, as you can see that the stress-strain profile follows the exact same pattern following the removal of the load after deformation has occurred, and the material or the tissue returns back to its original length. So there is no loss of material. Materials return to their original shape. Now, when we take a look at the bottom figure here, we have a stress-strain relationship that's quite a bit different. And so what we see here, we have a particular material that is placed under load, so it will naturally deform in response to that load. But at the very end, the very tip here, when that load is removed, we see that the tissue will start to return back to its original shape much quicker, because it's very steep here, and then it starts to slow down. Eventually, that tissue will return back to its original length, but there's a loss in that energy described as the hysteresis loop. And so the gray shaded area here represents that energy that is quote-unquote lost during the loading and unloading. So recall that a stretching or a deforming agent, some external load, has to apply mechanical energy that that's transferred to the material as it's loaded, and then once that external agent has been removed, then the energy gets returned, but not in a viscoelastic response. Internal tissue friction, because it is a fluid environment, will transform some of that input of that mechanical energy to heat, and then that will affect the rate at which the tissue returns back to its original length. And the gray shaded area is a reflection of that energy lost during the loading and unloading of a particular material. The next quality here that describes the viscoelastic response to tissues is something called strain rate sensitivity. And so if we take a look at the first two words here, strain, of course, when we talk about strain, we're talking about the relative change in shape or length of a particular material, but the rate is going to be an important factor here. So depending upon how fast we deform a material, it's going to demonstrate a very different type of response. So increasing the strain rate will have the effect of increasing the slope of the stress strain curve. And by increasing the slope, that increases tissue stiffness at higher strain rates. So the faster we stretch a ligament or some other biological tissues, it will present an increased resistance to that stretch. And to illustrate this, we're going to compare bone versus ligament. Bone strength, as a general rule, increases at higher strain rates than ligament does. So bone actually becomes stronger when the loading is applied at a very fast rate as compared to ligament. So because bone strength does increase at high loading rates, ligament tears are more common than bone fractures when that loading is applied very, very quickly. When the load is applied at a low rate, the tendency of bone avulsions occurs. Now, what a bone avulsion is that the bone ligament bone connection stays intact, and the bone fractures at the site of ligament attachment, and basically a plug of bone tissue is pulled off the parent bone. And so this figure here illustrates the relationship between loading rate, as you can see along the x-axis here. Here we see a very slow rate at which external forces are applied to a bone ligament bone specimen, up to relatively faster rates. And the probability of failure, or the percent of failure, we see is very high at very low loading rates, resulting in an avulsion type of injury. And so once again here, an avulsion injury is one where the ligament stays intact. It remains attached to the bone, but a plug of bone is essentially pulled off the parent bone. And that occurs at a much greater rate at low loading rates. And as the loading rate is increased from left to right, we see that the probability of an avulsion starts to decrease, and the probability of ligament tearing starts to increase, as we can see by the increase in the area on this graph. And at relatively high loading rates, there's what also exists is the combination of avulsion and tearing, although a mid-substance tear of a ligament is certainly more likely at high loading rates than a combination of tearing and avulsion, although that probability still exists. When we talk about the application of stress over time on this figure here, so what we're looking at here is maximum strain and maximum stress applied within the elastic range of a ligament. And so when we apply a particular, what we have here is the stress relaxation response to a ligament or to any other biological tissue when it is held to a fixed length. And so stress relaxation is another viscoelastic response here when we apply a maximum strain and maximum stress within the elastic range. So on the left hand side, this is the elastic range. We stretch a particular tissue or we compress a particular tissue to a fixed length and hold that fixed length. What happens is that the stress that the tissue will have a rapid decrease and will hit a new plateau. So the further resistance to stretch will start to decrease in this situation where the tissue has been held constant at that new length. When we do that, we see that the internal resistance to that that length will start to decrease. The tissue essentially starts to relax. There's still a stress experienced, but it's lower than the maximum strain and the maximum stress experienced within the elastic range. The next quality here is something called strain rate sensitivity that we initially described on slide 53. And so once again here, these are time-dependent properties. And so when we think about strain rate, it's the rate of strain as a function of time. So higher strain rate leads to greater and earlier stress. And so what we have here in one situation, so we're not comparing two tissues here, we're comparing the same tissue. So this could be a ligament or a bone or cartilage, that if we stretch that ligament or compress that cartilage at a particular rate, and the dot above the epsilon symbol here indicates the time rate in which that ligament is stretched or that cartilage is compressed, it's going to demonstrate that stress relaxation response. Now, in the second situation here, epsilon 2 with the dot on top, because this slope is steeper, what we're seeing here is that the same tissue that experienced the stress response here, hold it at a new length, and it demonstrates that stress relaxation. It will still experience stress relaxation. However, the stress that tissue experienced, the resistance to stretch, will actually be greater if we stretch it at a greater rate. And that's indicated here in the stress time slope. The next viscoelastic property that we'll discuss here on this slide is something called creep. And so when we think about something that creeps very slowly, we talk about moving. And in this particular case, the movement is a deformation. And so the strain response of a tissue is examined with respect to a constant external load, as opposed to strain rate sensitivity that we observed on the previous slide, where we held a tissue to a constant length. What we're doing here is we're holding a tissue to a constant external load. And so what happens is that with time, the tissues elongate asymptotically. And so the tissues don't elongate or compress if it's cartilage, for example, indefinitely. It reaches a plateau with time. And that's illustrated here on this graph as we examine time, and we apply a constant external load. And so as we ramp up the load, the tissue will experience a particular strain, and this is the end of initial loading. So the loading is not removed in this case, but it's held constant. And what happens is that the tissues will continue to stretch and will reach a new plateau, and this will take some period of time that will depend upon the tissue. And the difference between the length change at the end of the initial loading and the new plateaued length is what is referred to as creep. And this is also observed with what's called cyclical loading. And so in this particular illustration here, a ligament is subjected to repeated stress strain over time. And so what happens is that ligaments essentially soften. So there's going to be a stress relaxation response, not just with a single loading, but it's also observable with repeated loading. And so the peak force of a ligament, that resistance force to the stretching agent, will decrease as a function of time. And so this poses the question if exercising for a long time might predispose a joint to ligament rupture, because the ligaments would essentially soften over repeated cycles of joint movement. And so in this graph we see time in seconds in this sample illustration of a ligament that is loaded, and the ligament presents a resistance to that external load. Then the load is removed, and as the load is removed, the ligament will not present any resistance, of course, so the internal stress will decrease. Once again, here we're measuring force, so when we talk about measuring stress in ligaments, it's very difficult to do that, particularly under these cyclical conditions. But what we see with repeated loading, we load again, ligament generates resistance to the stretch, it's unloaded, resistance goes down, and this happens repeatedly. But if we examine the peak resistance to that loading, we see that the resistance will start to decrease over time, potentially allowing a greater stretch in that ligament with repeated cycles. So this ends this lecture on the basic viscoelastic properties of biological tissues, and the next lectures will focus on some clinical applications and the results of various studies.